Welcome to computer programming. This is a test for native data types. And we're going to look at the accuracy of some data types. This is relevant for all languages that use the numeric processor on the CPU. And we're going to set a breakpoint and step through the code. And we're going to start with floats. We're using Java here, but again, it applies to other languages. This float is a 32-bit float, and we're going to look at implementing currency with cents. So we're going to take $1 and we're going to add 1 cent. So that gives us $1.01. No problem there. We take $10, add a cent. No problem there. So we look at $100 and we add 1 cent. We get 101, but we also get a little bit more. We get 2/millionths of a dollar. Now let's take 1,000 and add a cent. Again, we get $1,000 and 1 cent. But now we have 10/millionths of a cent. Let's take the next step. Start with 10,000, add a cent. Now we have something less than a cent. We have $10,000.009766. So we're getting some inaccuracies with some fairly basic numbers. And with 100,000, again, we get something less than a cent added on. And this is because floating point can't be expressed accurately with decimals. But that's for another lesson. And at $1 million, it doesn't even add a cent. It just ignores the cent that we added. And for 10 million, obviously that's going to result in nothing added as well. So let's take a look at another case. Let's just add $1 to some values. So we're adding $1 to $10 and we get $11. Not a problem. $100, add $1, no problem. 101. 1,000. Same thing. 10,000, same thing. 100,000, a million, 10 million. And at 100 million, trying to add $1 doesn't do anything. And at 1 billion, it doesn't add anything either. Okay, so you can see that there's inaccuracies using floating point, especially with the 32-bit floating point. Now, we've got 10 million, and we're adding $1. And we're going to check to see if that actually equals 10,000,001. So we're doing a comparison. We've added $1 to 10 million, and we're actually comparing it to 10,000,001. And that results in true. That's good. Let's take 100 million and add $1. We're going to compare this to 100,000,001 as a literal. And it's true, which is good, but it's true for the wrong reason. We look at this, and this is 100 million. We're comparing it to 100,000,001 because this second 100,000,001 actually gets converted to 100 million, and that's why it's true. Let's do another compare. We're comparing the 100,000,001 to 100 million. And again, this is true. And it should be false because 100,000,001 should not equal 100 million. But again, both are rounded to 100 million. Okay, let's look at another problem. We have 0. We're going to add 0.1 1,000 times. So 1,000 times 0.1 is going to be 100. I'm not going to bore you, so I'm going to set a breakpoint here so we don't have to step through it 1,000 times. And we're just going to go run to. If we look here, this says 99.99905. So although this should be true, it's going to return false. So we added 0.1 1,000 times, we get this value, and it's not 100. although it should be true. Here's another operation. We're actually just going to multiply 1,000 by 0.1. We'll see what this value is. If we look here in memory, it says 100. And this is true. So that's good. That is accurate. But adding 0.1 1,000 times is not accurate. So the more calculations we do, the more rounding errors we get. Let's look at doubles. This is a 64-bit floating point value, and it's the same no matter what language because it uses the CPU to do the floating point. So we're going to do a similar calculation, 1,000 plus 0.01. And it shows up correct. 1,000,000 plus 1 cent. That's correct. 1,000,000,000 plus a cent, and that's correct. And 1,000,000,000,000 is correct. Now let's do 10 trillion, and that's correct as well. 100 trillion, not correct anymore. We get 2 cents added instead of 1. And with 1 quadrillion, again, we get no cents added. So that's an error. There's only so much accuracy with the double floating point. Let's try adding $1. At 1,000, we get 1,001, that's correct. And 1,000,000, that's correct. 1,000,000,000, that's correct. 1,000,000,000,000, that's correct. And 1 quadrillion, that's correct. And at 10 quadrillion, it's no longer correct. So let's take the 1 quadrillion, add $1, and compare that to just the literal. And it's true, it does that comparison correctly. And at 10 quadrillion, again, this is wrongly true because the value that we passed in is 10 quadrillion rather than 10 quadrillion and 1. And we're comparing it to 10 quadrillion and 1, but this value gets rounded to 10 quadrillion. So this is wrongly true. And lastly, we're going to compare the 10 quadrillion and 1 from X to 10 quadrillion, and it returns true because it's rounded this one to 10 quadrillion. Let's do the same calculation of 0.1 added 1,000 times. Again, I'm going to set a breakpoint here so I don't have to step through it all with you. And we're going to run it. And we look at this value. It's very close to 100, but not exactly. And it returns no. Even though it displayed 100.00, the actual value is 99 point a whole bunch of 986. So that's not exactly 100. Again, let's try this 1,000 multiplied by 0.1, and that returns the correct value. So another way to implement currency is to use integers, and the integer will represent cents rather than dollars. So here's $1, and we add a cent. And when we print it, we divide by 100 for the dollar part, and we use the remainder for the cents part. So we get 101. And this works for $1,000 and 1 cent, $1,000,000 and 1 cent. And this integer is a 32-bit integer. And we get $10 million and 1 cent, and that's about the maximum that we can do with integers. But you can see that it's far more accurate than the float. If we scroll back, we look at the float, has already had a problem at $100. Okay, we'll add 1 cent 1,000 times. And we're going to not do the loop. Toggle the breakpoint and run. And you can see we have 1,000 cents, so that's $10. And it will pass this test. Let's look at a long. This is a 64-bit integer. So we'll do the same operations. $1, it's fine. $1,000, fine. $1 million, fine. $1 billion is fine. $1 trillion, quadrillion dollars, and $10 quadrillion, and it's still fine. And again, let's do the loop and run. And we get $100 is equal to $100. So you can see that there's caution that's necessary when using floating points. And it's very dangerous to check for pure equality. One way to handle floating points, if you're going to use them, is to check for a range. And that concludes this lesson.